In today's lesson, we are looking at exponential models with differential equations. So this first part is just kind of an introduction to the lesson. So here we're starting, that is the general form of an exponential function. And we're going to start, I'm going to take the derivative of this. So dy, and it's with respect to t, is equal to, so let's see, do you remember how to take the derivative of exponential function? It's a times b to the t times the natural log of base b. So as you can see, y repeats. So I'm going to rewrite this as dy over dt equals, this is the same as y times the natural log of b. And now if you think natural log of b, that is a constant. So I will rewrite this as dy over dt equals a constant k times y. So what we're going to be doing is, if you can recognize this form, you know that we're referring to an exponential function. And if you remember back to Algebra 1 and Algebra 2, when you're dealing with exponential functions, we talk about growth and decay. And in this case, if our k value is greater than 0, it's referring to exponential growth. And if k is less than 0, it's referring to exponential decay. Okay, so now over here, here's the differential equation. In that form, we're going to do separation of variables. So I'm going to bring the y over to the left, 1 over y dy equals, so that k over here and multiply by dt. So now I've got the integral on both sides. So I'll have natural log of the absolute value of y equals k times t plus c. And then this will be, if you remember, y equals e to the power of this kt plus c, but then that c comes down in front. So I'm actually going to give myself a little bit more space. So I have c e to the kt. So when we have differential equations that start in this form, they're going to end in this form. So the c is going to be referring to our initial amount in our story problems. And then the k, we've already discussed, the k is that kind of that growth or decay factor. But the idea is that we can skip these steps and just always go straight from this form to this form. So here are two examples. So starting with the differential equation and then putting it into this form. So if you recognize this, so there's the k. So y equals c e to the 4 times t. And then this one, y equals c e to the negative 2 times t. And then if you're given additional information, like the initial conditions where like x is 0 and y is 5, you could plug that in and solve for c. So 5 equals c e to the power of 4 times 0. Well, this will go to 1, and you divide by 1, so c equals 5. So remember how I talked about that's your initial, and which would also be that kind of that y-intercept, the number that matches up with 0. So in this case, it would be y equals 5e to the 4t. All right, so now here is an example. It says 80 milligrams of a drug is given. And the idea is you're getting some sort of medicine and your body is processing, it's in your blood, and then you start to get rid of it. So the rate at which a drug leaves the body here. So we're starting, our initial amount is 0.80. The amount of milligrams in the blood after a certain time, so there's the function A of t. So we want to find that A of t. And we know the rate. So we know this differential equation. So we have this differential equation that's starting like this, and it's going to therefore end like this. So we're going to take the information that we need. And in this scenario, our initial amount is 80. That's our C value. And this is the decay factor. So the medicine is decaying. That is our K. So A of t is equal to 80 times e to the power of negative 0.07 t. Okay, and here's our last example. It says the rate of growth in the number of a certain bacteria is proportional to the number of bacteria at any given time. So right away, when you see rate, you have to think, okay, differential equation, proportional, that is that dy over dx equals k times y. Then it says initially there are 100 bacteria. So initial times 0, there's 100. And then 2 hours later, there's 150. Find an equation for the number of bacteria B at time t hours. So we know, let's change this. We've got dB over dt is equal to k times b. So that's the differential equation. So that means your answer will be in this form. So b equals c e to the kt. And then let's see what kind of information we have. Let's see, we know c is 100 because that's the initial amount. And then we don't know k, but we know a t and we know a b. So let's plug all that in. 150 equals 100 e to the 2k. And now let's solve for k. So divide both sides by 100. 1.5 equals e to the 2k. Take the natural log of both sides. So the natural log of 1.5 equals 2k. Divide. We could try to keep this inexact, but I'm just going and getting a decimal. And that decimal is, k is approximately 0.2027. So sometimes we'll stop right there. Like the question will be, hey, what is k? But this question actually says find the equation. So let's go back here. And the bacteria is equal to our initial amount times e to the growth factor, 0.2027 t. So based on the information given to us, that is the equation that's representing how the bacteria is growing. So there is your full lesson relating differential equations to exponential models. Good luck.